Kamusta? Mabuhay mga tao dito. Today we'll be reading 3.1 Chain Rule.
All right, thank you, JJ. All right, so Magandang Umaga. Today we are going to knock it out. And chapter 3 as a whole, its name isn't really that meaningful. Chapter 3, the next, how many sections should we see? 6 sections, 5 sections, 4 sections. There's some stuff in here that's only BC, so realistically it's 4 sections. Okay, chapter 3, we get some more derivatives. More about derivatives specifically. Okay, now in our world so far, we have only seen a few different types of derivatives, and we reviewed those just a second ago. In 3.1, this section takes 3 to 5 days. There's a lot of stuff in here, but it sounds like the coolest section ever. We get to start discussing what we will lovingly refer to as the chain rule. All right. Now, for the chain rule, the real big deal about this is when we're looking at chain rule, we're going to review some old stuff real quick. Do you guys remember ever talking about composition of functions? Okay, so this is not really calc stuff yet, but we're going to make sure we do a little bit of review. So we'll do a recall. Let's write two nice functions, and they'll be pretty chill functions. Let's say we have f of x equals, I don't know, trig or not trig? Okay, so let's say it's the square root of x, and g of x we'll say is x squared plus 3. So we just have two new functions. For each of these, we could differentiate them. This one might be a little bit harder if you don't remember the exponent rules. How could I write this as an exponent? X to the 1/2, whose derivative would be 1/2 x to the negative 1/2 then. And we can differentiate each one individually. Okay, if we do this, I want your guys' help. I want you to find two things for me. I want you to find f composed with g of x. And maybe we'll do this one together in case you're rusty. Okay, this notation should, I hope, look familiar to everybody. Fog and gone. Now, there's all sorts of stuff. Does anybody remember what we use these for? And that's okay. When I think of compositions, there's a million places and a million answers that I would have accepted there. I think of inverses, is what it makes me think of. If they're inverses, they spit out x when I compose them. Okay, and that's a pretty handy thing to be able to check. There was a problem on the first test that had is the inverse continuous and blah, 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 and that shows up with this stuff. But right now, very first thing, if I want to evaluate f composed with g, that notation there is ugly. Is there a better way to write it? F of g of x. Now, I think last year I probably changed the color over and over as we were doing this, and I will eventually, but I'm not going to do it right this second. F of g of x is the immediate first step that we rewrite this. And all that means is on my next line, I would say, well, this is just f of, and what's g of x? X squared plus 3. And we're just going step by step, right? If I wanted to do f of x squared plus 3, all I need to do is look at my function named f of x, which is right here, and anywhere there's an x, I'm going to replace it with a what? An x squared plus 3. So it becomes the square root of x squared plus 3. Okay, we're not going to make, the lesson isn't about this. Does this look familiar and okay? Okay, here's what we're after and where the chain rule is going to immediately begin to click in. If I hadn't given you any of this other stuff, and I said, here's a function, can we recognize that it is a composite like this? Can you, and it'll take some practice, and it's going to be easier for me to explain. But if I know that the square root of x exists, whether I write it or not, and that this exists, I think there's a composite function happening here, whether we're aware of it or not. Now, with this, it makes it really easy when we give all this. What is the inside of this? And I'm going to put this in parentheses, or quotations rather. What is the inside piece of this expression? And because we saw the other pieces, maybe it's easy. X squared plus 3. So either g of x or, if you'd rather, x squared plus 3. Do you guys agree that that could be considered the inside of our composition? Now, super clear here because that's just what g of x is, and it's literally on the inside. But if we looked at this without the other stuff, if you recognize that there's more to the square root than just x, we can identify that this is the inside as well. And that takes some practice to get used to, but we'll get there. If that's the inside, what's the outside? Good. The outside of this is that function f of x, or it's just the square root of x. And these are really compositions. Now, being able to pick this out takes practice. Is really weird to explain, but with a couple of problems, I think you'll start to be okay with it. And easy enough to identify once we get a little practice. Now, what we're going to start doing is we're going to use what's called the chain rule, obviously, to start differentiating things of this nature. Now, this one we can take the derivative of, no problem. This one we can take the derivative of, no problem. This one you might think you can take the derivative of, no problem. Here's my challenge. I'm going to give you a second. Whatever you think needs to happen, I want you to try it. Do it in your margin. You're probably going to put an X through it because, no offense, if you've never done calc, you're probably not going to be right. Try to take the derivative of this right here, and then I want you to ask your calculator and see if we get the same thing. Okay, so I don't know how you're going to do it, but I'm curious. Try the derivative and then check it on the calculator. Those rules that I erased on the board, right? Like they don't work quite right. So we're going to define the chain rule, and I know it's going to be redundant, but we've already done some writing. So let's give ourselves a lovely definition. So here we go, the chain rule. And today, tomorrow, the next day, we have a ton of examples. So here we go. We're going to do this very rigorously. So to begin with, let g of x, so we have some function, let g of x be differentiable, which I'm going to shorthand with diffable. That just means we can take the derivative at x. And more than that, we're also going to make sure that f of x is differentiable at f of g of x. Okay. In this situation, we then can take the derivative. And we're going to see it in two notations. We're going to see the prime notation, but we're also going to see the Leibniz dy dx notation. Okay, so the first one, if we're looking at this, we can write, and I'm going to put asterisks and I'll even change colors with this. We have two functions that are composing. That's all that's on the board right now, and we can differentiate it there. If we want to take the derivative of f composed with g prime of x, then here's how it's going to work. Now, I'm going to add some words in here real quick. What's the inner function? G. What's the outer function? F. Is everybody okay with how we're making that determination? Inner, literally more close to x here. When we do this, here's how we're going to take it. We are going to take the derivative of the outer function, f prime. That's my outer function. And then check it out. We're going to look at the inner function, but we're not going to touch it. F prime of g of x. But we're not done. There's one more little piece. Notice I've taken the derivative of the outside so far, and I didn't touch the inside. I'm now going to multiply it by what's the only thing left your gut says to differentiate. So notice this isn't times. This is f prime of g of x. I took the derivative of f. Let's take the derivative of g. Here it is. Okay. This rule does not have a nice sing-songy version. It's f prime of the inside times the derivative of the inside is how I look at this. Okay. It takes practice, but I do want to make sure we have a different notation as well. And this one works the first time. It's so silly. Y, let's say that this is f of u. No smirks this time. There's one. Okay. F of u. Okay, and beyond that, if we wanted this to look like a composition, we could just make u a function g of x. Now, we're going to pause right here. We're using notation to try to help, and there's a possibility that it does the exact opposite. If we did f of u, it is f of g of x, right? It's the exact same as the composition. We're just writing it a little bit differently here. Now, if I want to then take this derivative, we could say the derivative of y with respect to x, that's dy dx. Notice that stuff is weird, because what's the variable that we have written for this function? There's no x in it, but we're trying to take the derivative with respect to x, right? Okay, now this, it bothers me in two different levels. One, this notation is super duper nice. That part doesn't bother me. It works really, really well. What bothers me about it is the way that it works is not the way that it looks like it works, but we're going to treat it like that. And that's a weird statement to make. Check it out. The chain rule in this regard says, hey, just take the derivative of that function y, which it shouldn't be to x, it should be to what? To u. So it should be dy du times, then we're going to take the derivative of this thing, which is the function u, right? So we'd say du, and this would be with respect to which variable? X. So with this, we see the same rule written twice here, but this one's a little bit harder to see. Now, it looks like, and this is the part I want to stress, these just look like the regular fractions, right? And when you multiply these together, what happens with these du? It certainly seems like with fractions, it would just turn into 1, right? Okay, here's the part that bugs me. It does, but it doesn't really truly work just because they're fractions. This is a convenient thing about the notation that was developed. It looks like it, we're going to treat it like it, but there is a lot of stuff going on that is far beyond what we care about here. There are entire doctorate degrees written around this little idea, which sounds crazy. Does it really work like a fraction? It's not really a fraction like it is, but are we going to treat it like it just is? Yes, the du's fall out and we're left with dy dx. Now, from here, I'm going to be honest, I like this rule more. This one makes more sense in my head. This one exists, and we could ask for either, but we have it. Okay, before we do any derivatives with this rule, on your homework tonight, I would probably make sure you have this rule written somewhere. Okay, here we go. Our first example, we're not going to do any calc. I want you to, I guess we will do some calc, but we'll make it two parts. So first one is identify or find what we call the inner and outer piece. And we'll do that part together. We'll do the whole problem together, at least the first one, and find derivative. Okay, so there's two parts to each problem. The derivative part we'll get to. The inner and outer piece is the one that I'm really most concerned about. Now, because we're going to be finding the derivative, I know you guys have it on your notes, but I'm going to copy and paste this down here just so that we have it available when needed. Okay, here we go. For our first lovely function, that we're essentially saying if it were a composite function, which they are, but they're not represented that way, what is the inner and outside piece? So here we go. Let's say f of x on our first one is equal to e to the power of x squared minus 2x. All right. For our first one, I made a comment a moment ago that the dy du format I don't really love. I legitimately do think it's easier to make sense of these. But it's entirely up to you. They're doing the same thing. Gut feeling on what the inner or outer pieces are. Talk with your neighbors for a second, get an idea worked out. I'll call on somebody, and then I'll present it a couple different ways. Legitimately, if you're struggling with it, I think if you could decide, like if we mix in notations and say, oh, well, what is the u expression that we would plug in? It gets a little bit easier. Talk it out. I'll come eavesdrop on your conversations. I'm going to use two different functions. You don't have to write these down, but because I've already used f, I'm going to say it's like g and h. Okay, if we look at this function as a g of h of x, which is ugly, and you don't have to do this, but it might help. I'm trying to view this thing as a composition like this. Okay, h is my inner piece. H of x, I think my inner piece is just going to be this x squared minus 2x. And I'm going to plug in x squared minus 2x in for an x in my bigger function g, which is, well, what's the only other part left? Sorry, I already wrote it. I should have not yet. E to the x. If I do this composition, I see there's an e to the x, and then I just plug this in for x. This is really a composite function. Now, if you don't like calling it g and h, don't do it. I'm fine with that. In my head, that e to the u question realistically is much easier to think about. Okay, now, because of the way it was presented, let's just knock it out. And I should have said that inner was x squared minus 2x. And outer was what again? E to the x. So let's go ahead and try to apply the chain rule for our first time. If you can wait 30 seconds, that'd be awesome. But if you're going to pop, you can just go. Okay, so let's try it. F prime of x. We are going to take the derivative of the outer function first. What's the derivative of e to the x? So good, but I'm not going to write x. I'm going to do e to the, and we don't touch the inner piece. I'm going to keep it the same. What was the inner piece? X squared minus 2x. Nothing crazy has happened yet. I'm now going to multiply by the derivative of the inner piece. What is the derivative of that inside piece? 2x minus 2, and we're done. We have a derivative. Okay, Riley, if you want to go, you can. Chain rule has been done every single time, and you don't have to do this example, but I do want to demonstrate it to you. E to the x could also be a chain rule. Here's the outer, it's e to the x, and the inner is just x on this one. It's weird to do it, but we could. If we took the derivative of the outer, it's e to the, don't touch this, x, times, what's the derivative of x? You've been doing the chain rule. I've just given you problems which this inside derivative has always been 1 up to this point. You've been doing it the whole time, just like every number you've ever dealt with has an I in it. It's just 0 of them, plus 0i. Exact same representation. Cool. All right. Now, as we get going, if you don't have parentheses, add them. They matter. If you don't have them, all you're multiplying by is 2x. Seems easy, seems hard. So let me rephrase that question. Are we doing another one together, or do you want to try one on your own already? Okay, on this one, I'm going to switch back to the other color of red. On B, we're going to say this time, I'm not going to give you a function. I'm just going to name it right off the bat. I lied, I'll call it y. I want the derivative after identifying inner and outer for the cosine of 3x plus pi fourths. All right, what I want you guys to do is before you commit to trying to differentiate this, check with me, let's identify the inner and outer. I'll give you a second, go with your gut. If you're wrong, we'll clean it up, it's fine. Here, inside, and it's nice with cosines and sines and logs and stuff realistically because the argument is very clearly the inner piece. This is a harder problem to pick it out. But essentially, and it doesn't always work, but if you could put parentheses somewhere to make the expression more clear, you've probably identified the inner piece. Okay, so outer is cosine of x, and let's just go ahead and find the derivative. I'm going to write it as dy dx this time, since I could do y prime, doesn't really matter. Dy dx. What's the derivative of the outer piece? Negative sine. And what do I do with the inner piece? Nothing. Don't touch it. Don't even look at it. Okay, you actually do have to look at it because you have to be able to write it down, but you get what I'm saying, I assume. Times, what's the derivative of that inner piece now? 3x. Now, we have the derivative. What I want to make sure that we do is all agree that this looks stupid. There's something we can change about this. It's not 3x. Delilah's already doubting me, and I could see it in her eyes, and I had to think for a second, where's my mistake? What did old Holloway do wrong? The derivative of 3x is not 3x, it's 3. And you guys might have even said 3. I might have said 3 and just wrote it. I don't know. I'm not sure. But now we can all agree that this still kind of looks dumb. Why? Maybe we can't. Of course we're going to move the 3 out to the front. That looks silly. I think this is just negative 3 sine of 3x plus pi fourths. Doable? All right, let's try another one. And then we're going to start getting all of our rules out. I want you guys to do one. Whether you write inner or outer is entirely up to you. I'm sure that I will write it or at least speak it. But here we go. Last one. Ooh. So check it out. F of u equals the square root of u. U, coincidentally, equals equals x squared plus 1. I want you to find me this chain rule. Find the derivative of f of u. So find, and I'm going to be more specific, d du, I'm going to say d dx, rather, of f of u. The notation has changed, and it feels a little harder. Does it feel harder? I don't know if it does. Maybe. Would it be advantageous or helpful, rather, to write this thing as a nice single function in terms of x? Okay, so if I did f of u, it becomes, and just to make sure, we'll write this as an f of x, so it gets a little bit easier to see. This is the square root of what? So square root of x squared plus 1. That's what f of u actually is. Now, I'm going to do one more step before I even think about taking a derivative. Radical symbols, as nice and pretty as they are not helpful for using derivative rules. I'm going to avoid them 90% of the time if possible. And I'm going to avoid them by using these lovely parentheses. And what's the power here? This is the only time you'll ever see me write the fractions with the diagonal fraction bar or vinculum. I'm okay with it here. As soon as we do this, and Riley, the only comment that you missed is, if you're going to put parentheses around something, pretty good chance that's the inside piece. Okay, now let's take the derivative of this. Inner and outer, just before. What's the outer function? Square root, and the inner is that x squared plus 1. So help me take the derivative of the outer. Or, if you don't want to have to identify those, can we all agree that that's the inner piece right now? So let's just differentiate and don't change that yet. What happens with the 1/2? So eventually, but that 1/2 moves somewhere. 1/2, that's the power rule. And then I'm not going to touch the inside. It's x squared plus 1. And Fern said it's now to the power of negative 1/2 because we just used the power rule. There's our first step. Inside, don't touch it, just differentiate around it. Now we need to multiply by one more thing though. I need to multiply this by something. What's the something I'm going to multiply it by? Almost. It's not just x squared plus 1. Why not? It's its derivative. What's the derivative of x squared plus 1? 2x. Now, the simplification thing. I wish that there were a solid rule that I could say this is exactly where you stop. There's obvious stuff that we can do, and depending on what we're doing with it, would dictate what changes. But the first things I see is divide by 2 and multiply by 2. They're gone. Which means I have an x. What's a negative exponent do? It goes to the denominator. Now, I think this is the one that we worked at. I'm going to change it back to a radical. It would be x squared plus 1 to the 1/2 in the denominator, or just x squared plus 1, like this, which I'm pretty sure is what your calculators told you on the one that we looked at when we started. Okay, these things take practice. The good news is that once we kind of understand the basics of the chain rule, then the rest of the rules come out really easy. Tomorrow, we will be making some flashcards. You don't have any homework tonight. Cool. I'll have your test graded hopefully at lunch. We'll go over them and hand them back tomorrow.